All right, so now let's talk about the derivatives of my trigonal bipyramidal. So now I need to put an electron. So one of these is going to be an electron. And so instead of it being a bond, I got to pick. But I have axial positions and I have equatorial positions. So I need to know what is the best choice. So let's look at the next slide so it'll help me know. If I put the lone pairs here, then I would be 120 from two things. So here to here would be 120. So I'd be 120 degrees away from two things. And then from here to here would be 90. And so then I would be 90 degrees from two things. Say I put it in the top. In the top, I'm not 120 from anything because I'm in axial. So axial is only 90. So here I'm 90 degrees from three things. So if I put it in the axial position, I'm closer to more of the atoms than if I were here. Here I'm only 90 degrees from two things. Here I'm 90 degrees from three. So we don't want to put the lone pair in the axial position. The lone pair is always going to go into the equatorial position. Okay? So lone pair always goes into the equatorial position. All right, so let's go back. So here it is. Here is my trigonal bipyramidal. And so not the axial, but the equatorial. So he becomes a lone pair. Make him a lone pair. All right, so here's my lone pair. Now, how we figure out what this is, if I were to tilt it a little bit like this, this actually looks like something you might have played at in kindergarten that went doop, doop, like this, up and down, side to side, like this. It is a seesaw, okay? So the shape width still got 5, because remember our parent group is AX5, but 4 bonds in one lone pair. This is called seesaw. And it also has 4. So sometimes they call this because it's 4 and it's just kind of a little bit funky, a distorted tetrahedron. Okay, so let's look at that one. So here's the seesaw. So I would have 1, 2, 3, 4, 5 things. So my parent geometry is going to be the trigonal bipyramidal, but one of those electrons, lone pairs, goes right here in that equatorial position. And so if I were to take this and flip it down, it kind of makes a seesaw. So think about like this is the fulcrum. I sit here, and these go up and down, you know, like a seesaw. Okay? So that is my shape there. So let's talk about the angles. So usually the angles, here I could go here. Usually the angle from axial to equatorial is 90. So remember, it's whatever the normal would be less than. So here to here, axial to equatorial would be less than 90. And then equatorial to equatorial is usually 120. It would be less than 120. So axial to equatorial is less than 90. Equatorial to equatorial is less than 120. All right, let's do the next one. So now, instead of having just one lone pair, I want another lone pair. Well, I can't go in the axial position. It has to go in the equatorial position. So make it in the equatorial position. Okay? And then if I tilt this, what letter does this look like? It looks like a T. So we call this one T-shaped. So it would be still 5 things total, but it's 3 bonds and 2 lone pairs. And we call this T-shaped. So let's look at that one. So this would be the Lewis dot structure. 1, 2, 3, 4, 5. Parent group is trigonal bipyramidal. See, trigonal bipyramidal is that electron geometry. But I put 2 lone pairs in that position. And so now I get this T-shaped. Okay? And I have the T-shaped on this slide so you can see a little bit, like you could see if I turned it, what it would look like. So 1, 2, 3, 4, 5, trigonal bipyramidal, but it's a 3 bond, 2 lone pair, 3, 2. And so it makes this T shape. But this T, the arms of the T is not straight out exactly like this because you've got lone pairs right here. So those lone pairs push, and so the arms of the T are kind of like a lazy T. So think about it as being a lazy T. And these arms kind of go down because this has to be less than 90, okay? So remember, T-shaped, this is normally 90, but it's gonna kind of sink down and be less than 90. All right, so let's go back. Remember, we wanna get all the way down to only 2. So equatorial, lone pair, equatorial, lone pair, so all I have left is this one. So I make that a lone pair, and now all I have here is, what did we call this? Straight line, linear. And because my lone pairs, these guys are gonna push up, and these guys are gonna push down, it kind of cancels each other out. And so this is just a straight line, so this is just 180. So if I have 2 bonds and 3 lone pairs, this is linear, and so linear is exactly 180. It's not less than anything, because it's just axial to axial. So let me show you that picture. So here's my linear. So I have 2 bonds, 3 lone pairs, 5 things total. So my parent geometry is that trigonal bipyramidal. I put my 3 lone pairs in the equatorial position, and so all I have is linear. Here to here, axial to axial is 180, okay? And so that is going to be my derivatives, my subshapes for trigonal bipyramidal. On the next lecture, we'll do the subshapes for octahedral.